Welcome. In this session, for the SVM or support vector machine, we'll derive the dual formulation. Let's recall that the primal Lagrange function had this form, and from it when we required stationarity, we had these constraints on we could express the weight vector as a function of the data labels and the Lagrange multipliers, and we have a constraint involving the labels and the Lagrange multipliers. Let's now write that primal in a closely related form, and we'll simply expand these terms so that we can do some substitutions. So that is 1/2 of W transpose W, that's our objective function, plus, instead of using alpha transpose 1, because I'm anticipating the dual formulation, I'll rewrite that as 1 transpose alpha, or we could say the 1 form 1, and then minus, we can write this as alpha transpose YXW minus B times, and alpha transpose Y is the same as Y transpose alpha. To get the dual formulation, what we have to do is we take this expression for W and substitute it into every occurrence of W in the primal, and then W will disappear from the primal. And you might ask, well, what about B? Isn't that important too? And the answer is that from this constraint of stationarity for the primal formulation, this B will disappear. And so the dual will only be in terms of the data vectors, the data labels, and the Lagrange multipliers. Let's write that down. So the dual is a function only of the Lagrange multipliers. And that is 1/2 of W transpose will be alpha transpose Y transpose, but that's Y. X transpose transpose is X. And then substitute in W, that will be X transpose Y alpha minus alpha transpose YX, and now for W we substitute in X transpose Y alpha, and then this term disappears because of the stationarity constraint on the primal Lagrange function. Oh, and we're missing a term here, aren't we? We have to add our 1 transpose times alpha, and then here we now add our 1 transpose times alpha. There. So this slightly simplifies, because when we take this term minus 1/2 of the term, we end up with minus 1/2 of alpha transpose Y X X transpose Y alpha plus the sum of the Lagrange multipliers. Let's make an observation here. The first is that this is a concave function, and it's a concave quadratic function, and so it has so we know that we can maximize it. However, it's not an unconstrained function, and the reason is that there are KKT conditions that apply to this, and the most important is that in the dual formulation, a KKT point has to satisfy primal feasibility, and the dual feasibility first, and dual feasibility is that these Lagrange multipliers have to be 0 or strictly positive. So in the KKT conditions, we need dual feasibility, which is every Lagrange multiplier has to be greater than or equal to 0. Let's now consider what happens. So consider some alpha j at a KKT point. And what will happen is either, so if alpha j equals 0, then the constraint and that constraint was that yj times xj transpose w plus b has to be greater than or equal to 1, then the constraint is inactive. And we can underline that inactive. If a constraint is inactive, then I know for sure that that xj that corresponds to it is not a support vector. And the only other possibility is that if alpha j is strictly greater than 0, then the corresponding data vector is a support vector. And so this complementary slackness idea says that xj is either an interior point and its Lagrange multiplier is 0, or it's a boundary point. And if it's a boundary point, then that means that it's a support vector. And then to calculate B, use any active constraint. And so what we could do in the worst case scenario is we could go through all pairs of these and we could discover whether, or we could go through each one of these and we could discover whether or not it's a support vector. It turns out that any algorithm that does this would be quadratic in the number of data vectors. Now let's review what we've covered in this lecture. We stated the SVM primal. It's difficult to solve because of the inequality constraints. The dual is quadratic in the number of data vectors. If we only have a few thousand, that's not a problem, but when we have millions or billions, that becomes very computationally intensive. The sequential minimal optimization, or SMO algorithm, we didn't cover that, but it's a typical one that is offered as a default in MATLAB, and it's usually linear in the number of data vectors. What these combine to mean is that the SVM is in practice a reasonably efficient and often effective method for nonlinear data analysis.